Good afternoon. I would like to start by thanking the organizers for giving me the opportunity to present myself to the nano community at Tel Aviv University. I joined the Department of Material Science and Engineering at Tel Aviv University last October, and my talk will be about the synthesis and characterization of atomic films, specifically HBN and graphene. I will try to convince you why these materials are so interesting from the scientific and also technologically point of view. I will talk about the synthesis of graphene first, which is the most understood material in terms of synthesis, and then hexagonal boron nitride. I will show you how we manage to characterize such atomic heterostructures, which is also of great interest, to have heterostructures made of just atomic layers, few atom thick heterostructures with different functionalities. And then I will conclude. So most of you, I guess, you know these guys, Novoselov and Game. They won the Nobel Prize in 2010 in physics for the rediscovering of graphene. It's funny to think that the graphene, which is the building block for all the other carbon allotropes, graphite, carbon nanotube, and fullerene, was actually discovered or had a great interest only in 2004, while the C16 and the 616 was discovered in the late 90s, and the carbon nanotube in the early 90s. Sorry? Late 1980s, and nanotubes in 1991. And then, of course, the interest in graphene brought a lot of interest in other 2D materials, other 2D atomic films. And graphene is not the only one. Graphite is not the only layered material. This is a wide family with a lot of different types of materials. Here you can see a single layer of graphene, a single layer of hexagonal boron nitride, a single monolayer of MOS2, which is composed of 3 atomic layers. And this MOS2 belongs to a wider family, which is called the transition metal dichalcogenides, which is composed of a transition metal and sulfide or selenide or tellurium. And there are more exotic materials and very controversial, like the silicene, a single atomic layer of silicon in an hexagonal pattern, an hexagonal crystal structure similar to the graphene. And recent also there is a lot of interest in the black phosphorus. And there are others, other materials as well, with many different functionalities and properties. From being metallic, some of them are metallic, some of them are semi-metallic, and there are a lot of them that are semiconductors with very different band gaps, a lot of them in the sweet spot for many applications in nanoelectronics and optoelectronics. And there are also insulators like hexagonal boron nitride, which is a very wide band gap semiconductor, 6 eV electron volt. And the interesting thing about these materials is that basically they are all surface materials. The atoms, they don't have where to hide. And therefore, you may think of many possibilities to change and control their physical and chemical properties by functionalization or electric fields and so on. And this was proved theoretically, and also there are some experiments on graphene and also on other 2D materials. In the case of graphene, of course, it's very interesting. The mobility is just huge. The larger electron mobility that was measured in any material, it has huge thermal conductivity and is very strong. And of course, it can be used in many, many potential applications, from nanoelectronics, thermal management, NEMS, and so on and so on. And again, these materials are not new. Actually, in the 60s and 70s, many people, not many, but there are a few scientists that were very interested in studying these materials by many methodologies. One of them was by intercalating these layered materials with many other elements to change the properties, and also to try to isolate these materials, these monolayers. And even the mechanical exfoliation, the same so-called Scotch tape exfoliation that was used by Novoselov and Game in 2004, was used in the 70s to isolate, to try and isolate other layered materials. And also there were some attempts to synthesize them, but the results were not in the atomic scale, but in the tens of nanometers regime. So again, graphene was actually discovered as a single layer on top of metal. Was discovered in the 70s by Sommerjai and May, and then it was exfoliated in 2004, and then it was only in 2009 that was found a real good way to synthesize it in a large scale as a single layer in this case on copper, and I will discuss that here. And this opened up this field because then everyone with a relatively simple system can synthesize graphene, a single atomic layer on very large area, centimeter square area, or actually it depends on the size of your reactor. And on the copper, it led to very nice results. But when people used nickel, which is also another very common material to grow a few layers graphene, the results were very different. So on copper, you get usually a single layer. On nickel, you get few layers, or even ultra-thin graphite. It's not a graphene. Graphene is defined as a single layer of graphite. And the reason for that was found by the group in Austin that I joined a few years after this work. What they did is that they exposed the catalytic surfaces, the nickel, in this case, nickel foils or copper foils, sequentially by two different hydrocarbons. One of them that is composed of natural carbon, which is mainly C12, and the other one that was enriched with C13. And by exposing these hydrocarbons to the substrate, they discovered that on copper, the growth is mainly surface mediated, while on nickel, the carbon just diffuses into the nickel and then segregates out. And that's why all the C12 and C13 are mixed together. And that's why also it's so hard to control and to control the number of layers in this material. And you can see it here by these two isotopes. You can identify them very easily by Raman spectroscopy. What you can see here are the most common graphitic peaks, the 2D or the G prime, the G, and the D peak, which is not seen here because the graphene is of high quality. The D peak refers to a defect, and it has to be a defect to activate it. And you can see a very clear shift from the natural or the C12 graphene to the C13 graphene. And so then Raman spectroscopy was proved to be a very, very good tool to characterize these materials, to characterize graphene. And also to characterize as an XC2 system or methodology to characterize the growth of the graphene. And after you grow the graphene on metals, of course, on metals is not so useful. You need to transfer it. One of the most common ways to transfer it is by coating your, so you have here the copper and the graphenes, and then you coat it with a thin layer of polymer, PMMA, for example. Then you etch the copper and the polymer with the graphene. You need to transfer it to the target material, and then you just dissolve the polymer, and you end up with the graphene on top of your target material. This is a very common way to have graphene. So then when I reached the, when I came to this group, when I joined, before that. So this is another example of a way to show why CVD method is so important to grow these materials and so good, such a good tool to grow these materials. This is, by the way, a recent review in Nature Nanotechnology that shows the mobility as a function of the preparation method for two different materials, MOS2 and graphene in the red curve. Oops, sorry. As you can see, the best mobilities, so the best quality you can have by mechanical exfoliation, this one and this one. But then chemical exfoliation is here in the worst, as a worst case, the worst material that you can get is by chemical exfoliation. But then the CVD method is here, which is approaching, it is constantly improving and is approaching the quality of the exfoliated material, also in graphene, but also in MOS2. So CVD method turns to be a very good methodology to grow these materials and to have them in large scale with the potential to control the number of layers and maybe the composition, I hope, in the future. So when I came to this group, they told me, basically told me, okay, that's what we did with graphene. Now you take the same and do it for HBN, hexagonal boron nitride. You just need to change the precursor, take the same metals, and basically it needs to grow very similar. Well, it didn't, and I will discuss it in a bit. So why hexagonal boron nitride? Hexagonal boron nitride is, again, is a large bandgap semiconductor. It has very interesting properties, thermal properties, strong chemical resistance, etc. But the trigger for that was this paper in 2010 by the group in Colombia, where they showed that hexagonal boron nitride, which is also, to remind you, is a layered material very similar to the graphene, in the case, in the sense of the lattice, but instead of carbon, you have boron and nitrogen atoms intercalated. So they show in these papers that hexagonal boron nitrides, few layers hexagonal boron nitrides, are the best support material, the best so far support material for graphene electronic devices. And why is that? Comparing it to more classical materials such as silicon dioxide or hafnium dioxide and so on. Because the hexagonal boron nitride is a crystalline surface, in contrast to the hafnium oxide and silicon dioxide. It has no dangling bonds. It is atomically flat. It removes very efficiently heat created by the device. And there are other parameters as well, but these are believed to be the reasons why basically the mobilities measured on devices on hexagonal boron nitride are an order of magnitude or even 2 orders of magnitudes larger than the ones measured on silicon dioxide or other substrates. So then we started to grow, and here you can see this is among the first growth. Here you can see an optical image of a transferred few layers film. This is just the Raman characterization. I will talk about the Raman of HBN. This is the Raman peak of HBN. In contrast to the case of graphene, here you don't have many peaks to deal with. You have only one peak. You don't really get many information from the Raman here. And this is the this is the TEM and the lattice of the HBN, also observed TEM, showing that we have the material, we have a few layers. We don't really understand why it grows as a few layers, but we will in a second. But more interesting, we could see that we can control the number of layers. We can control the thickness just by changing the time, the growth time, which, as you can see here, from A to D, from just a few layers to 100 layers or even more, just by changing the growth time from 1 minute to 30 minutes. Now you may think, okay, this is common in many growth types. When you grow a thin film, if you grow it for a longer time, you will get a thicker film. But this actually is not the same case, because we are talking about layered materials that are, they have, as I told you before, actually it's very hard to grow an HBN on an HBN. It's very hard to grow a graphene on top of a graphene, because it's not reactive at all. It's not like growing a regular thin film. The growth mechanism is totally different. So one of the answers for that could be that we have just a case of a surface, of a diffusion into the bulk of the catalyst and segregation out, as in the case of a few layers graphene on nickel. But then when you look at the phase diagrams, you notice that according to them, there is no solubility, not of boron, not of nitrogen. So you should not have any diffusion into the bulk. And so we didn't really understood what's the reason for that. And we made more experiments. Here you can see, for example, again, a thick film of HBN. This was a growth that was done on two different substrates at the same time, on sapphire and on nickel. And you can see that the thickness and the structure is very different, although both of the substrates were at the same CVD growth. And the reason for that came out with other series of experiments in which we, instead of using foils, we used thin films of different transition metals. And what we notice is that even though, according to the phase diagrams, there is supposed to be no solubility, we do see diffusion into the bulk and segregation out, as you can see here, for example. Here you can see a thin film of cobalt. This is the cobalt. And this is on top of silicon dioxide. And after the growth, you can see the cross-section TEM image showing on top of the cobalt that you have that we have a relatively thick layer of HBN, but we have also HBN at the interface between the cobalt and the silicon dioxide, meaning that we have some diffusion into the cobalt or nickel, which are very similar in this case, and we do have diffusion and segregation. So then, okay, so we said, okay, on nickel it grows similar to the case of graphene on nickel. It diffuses and segregates out, and we were looking for other materials as well. Also on copper, it grows as a few layers HBN. And so how do you control the number of layers on HBN? How do you grow a single layer? Is that possible at all? So before I talk about this slide, just a brief introduction. Few reports on graphene, not few reports. One report on graphene, they managed to control the domain size of graphene by using what we call a copper pocket or a copper enclosure. It's basically a copper foil that you fold it together, you close the edges, and because of different reasons that I will not explain today, the domains, the crystallinity of the graphene inside the pocket is much larger, 1 order of magnitude at least, than in the outside, in the exterior of this enclosure. So we did the same with the nickel and copper for HBN, and it didn't work. But when we introduced inside these pockets and closures some carbon, or when we did these growth experiments with some hydrocarbon flowing in the chamber, what we noticed is that we did get inside the pockets amazing single or bilayers, as I will show you soon, domains and continuous layers of HBN on nickel. What you see here, the dark areas are the HBN-coated nickel. You can see isolated triangular domains. They grow triangular domains because the nitrogen edges are more stable than the boron edges. And here you can see a dark field optical microscope image. We can, in principle, get a lot of information from that. And the reason is that the copper, also nickel, after annealing, they have nanofacets. But these nanofacets, if they are not covered and protected by graphene or HBN, they are just destroyed by oxidation. By oxidation. So this is a way to know right after the growth when you have a material or a very thin layer coating your nickel, just by seeing these nanofacets. So in this case, we have a continuous film. In this case, we have an isolated domain. And STM shows you that it's atomically flat, and you can see the lattice. So why is that it grows that way? How it grows on a nickel by using this pocket with the carbon as a single layer, but it didn't grow as that on a flat sample. And the reason for that is that the nickel there is some oxygen in this system. There's some residual oxygen, so the nickel is a bit oxidized. When the boron reaches the nickel oxide, it reacts, it reduces the nickel to form boron oxide. When the boron oxide is formed, that's it. The boron is killed, and it cannot form HBN. But if you reduce the boron, you cannot reduce, by the way, the boron oxide with hydrogen, as you can do it to the nickel oxide. But when this boron oxide reacts with carbon, it is reduced by a carbothermal process, so it can react with the nitrogen to form this BN. So this boron oxide fixes the boron at the surface of the nickel and stop it from diffusing into the bulk, so then you get only 1 or 2 layers. And how... Okay, this is not shown. Okay. How do we know that it is true, that this is the case? So we did a lot of XPS and top SIMS characterization. We don't have much time here, but I will try to explain this slide. What you see here, every row is a different sample, and every column is a different element in XPS. Sorry. So the first sample is an interior of a pocket without any carbon. The second sample is the same, but with a bit of carbon and some HBN domains, isolated domains. The third one is almost a full layer, and the last one is the best film, the complete full layer, higher quality. And you can see from following the B peaks that in the beginning you get only the boron oxide peaks, but then as the HBN improves, you start to get some BN peaks, and then you get only the BN peaks, and then actually the same with the nitrogen peaks, and the oxide, the oxygen and the carbon amounts actually are heavily reduced along with the quality of the HBN. When the HBN is fully covering the nickel and is of higher quality, you get less amounts of oxygen and less amounts of carbon. The same conclusion you can reach with the top seams, but I don't have time now to explain that. And I will also just say a few words about this. One of the problems with HBN is that there is no real good way to characterize the number of layers of it. It's not like the graphene that you can do Raman spectroscopy on Raman mapping and you get a very nice picture of the number of layers, doping, strains, and et cetera, et cetera. With HBN, it's not the case. So we managed to collaborate with Professor Frinstra from Carnegie Mellon, and he did for us some LEEM and LEED. And actually, LEEM is a very good system, very good way to do that. Here you can see an area of a diameter of 25 microns. And according to the spectra, different spectra, I don't have time now to explain that, but you can identify where you have single layer, bi-layer. You can identify up to 6 or 7 layers. I will skip that. As I told you before, heterostructures, atomic heterostructures are also of high interest. The reason for that is very obvious. You may have an ultra-thin film which is composed of very different materials with many different functionalities, but there is no real way, no good way to characterize these heterostructures, in special when you synthesize one on top of the other, that you can have, that you need a good way to characterize the chemical composition and the phase of this material. And there is not such a way to do that in the 2D regime. So we did it. We did some tries with. We did some experiments with top seams, and top seams is very promising for that. If you do it right, and if you do it very mildly, you may have atomic resolution in the vertical, quasi-atomic resolution in the vertical direction. Here you can see 2 different samples. The first, this is a graphene on top of a single layer graphene on top of a monolayer MOS2 triangular domains, both of them proved by Raman. And this is a single layer graphene on top of few layers HBN. So the red represents the carbon, the green here represents the sulfur, here it represents the boron, so the boron nitride, and the blue, the oxygen in both cases. And we can see that after only a few seconds of very mild sputtering, we can erase, get rid of the graphene, of a single atomic layer of graphene, and then remain with the MOS2 to study it, and here the HBN. And when we do it, we can see that we can identify at very stage, and we can reconstruct the stacking of the different layers, but also the impurities that are within the layers. These layers, by the way, were prepared by transfer, CVD and transfer. And when you transfer, you introduce a lot of impurities which are related to the process. And we can actually track the impurities according to the process done for the heterostructure preparation. So my conclusions would be that in order to synthesize single layers, in order to control the single layers, and not only the phase of the single layer, but also the composition, you really need to understand the growth mechanism. You need to control it. You need to find ways, especially for the case of TMDs. I didn't even talk about the TMDs here, but we need new methodologies to synthesize them and also to characterize them. So there is a lot to do. And okay, I will finish here. I just say that I'm looking for students, master, PhD, and postdocs. So you're welcome to find me. Here are the details. And also in in July, we are going to have a very nice conference on this topic. So if you're interested, please come and join. It will be in Bar Ilan, July 7th to 9th. And these are the confirmed invited speakers, which is a very nice and partial list, I may say. Thank you. When is the barbecue? That's what they want to ask. Yes.
Next time, probably. Okay. Thank you very much.
Sure.